Hello students, welcome to chapter 11. This is all about motion and the science of motion. So you're going to do a little note taking here. Please take out your notes. You start off with a blank piece of paper. There's some stuff that you can skip that you don't need to write, other things that you will absolutely need to write, and I'll tell you what to write. As always, because it's a video, obviously you can pause it if I'm talking too fast and write down what's on the screen and then hit play and go from there. All right, so the motion notes. Motion, defining motion, measuring motion, and then changes in velocity. What exactly is velocity? All right, so motion. Technically, our definition of motion is the change in position of an object. Right? The change in position of an object is called motion. Now, really, how do we know something is moving? That may sound like a silly question, but it's not necessarily an intuitive answer. We say something like, oh, we know it's moving because we can see it moving, but how do we know that it's moving? And really, it's probably never thought of this before, maybe you have, but to describe the motion of something, you compare it to something that is assumed to be stationary or something that is stationary. So really something, you can tell something is moving measured against the thing that is not moving. Right? The background we use to describe the motion is referred to as, let me get myself out of the way here, is referred to as the frame of reference. So the frame of reference is how you know that something is moving. If you just imagine a white background, and a rocket ship, and that rocket ship was moving across that white background. Well, how do we know that rocket ship is moving? Let's take a look at a short video to see what we mean. All right, so we're not going to watch the whole thing, but we're just going to watch it for a few seconds. You're just going to see a dog. Here we go. Right. Shiny little music. All right, so how do we know the dog is moving? Well, if we reference it against the things in the background, right, we can tell that the dog is moving. Now imagine we didn't have the trees going by and the dogs was approaching. It would just look like the dog was just stepping. So again, it's because the dog is moving with respect to the objects that are in the background. That's that frame of reference. That's what we mean by that frame of reference. All right, so back to this. How do we know the dog is moving? Again, because of the background.
Welcome to our solar system. Below you will find our sun. Our star is 2 octillion tons of hot hydrogen gas emitting 400 centillion joules of energy every second. The hottest part of the...
Let's get that out of there. Sorry about that. All right, so how do we measure motion? Again, you should definitely be writing these things down. How do we measure motion? Well, we know the measurement of motion is speed, how fast the position of an object changes with time. It's not just how fast it's going, or it's not the distance it's covering, it's the distance it's covering over time. Like if I said I was going 60 miles, that's a distance, but that's not a speed. 60 miles what? 60 miles an hour? 60 miles a second? 60 miles a day? So it's always referenced to a distance and a time. All right, so it's a really simple formula that we use for this relationship. Speed equals distance divided by time. Speed is distance divided by time. So again, if you need to pause from time to time to catch this and get this all written down, please do so. And I do want you to, and draw it relatively big, I do want you to draw this graphic. So we really have three components to the equation. We have distance, we have time, and we have the speed. And if you know any of the two, you can figure out the three. If you know any of the two, you can figure out the three. Right? So, and again, yes, put this little divided sign in here, put this little divided sign in here, and put this little times sign in here, because that clues you in how to figure out one or the other. You can be given the distance and the speed, and you can figure out the time. You can be given the time and the speed, you can figure out the distance. You can be given the distance and the time, and you can figure out the speed. And if you set it up this way, then we can follow these three simple graphics. Right? You don't have to draw this again. You don't have to draw this triangle again, but I do want you to write down these three formulas. Look, speed. Speed equals distance divided by time. Right? So speed equals distance divided by time. So these are the speed and the time are flipped around here compared to this one, but it doesn't really matter. Right? Let's look at distance. What does distance equal? Distance equals speed times time. Right? So distance equals speed times time. And then lastly, what is our time? Our time is distance over speed, or distance divided by speed. So for sure, write all three of those down, and for sure, draw this little triangle. So again, you'll be given, we'll look at a couple of sample problems. You're given two of the three, you can figure out the third. Calculating speed. All right, so go ahead and write this down. Write down calculating speed. You don't need to write the formula down again. Here's the problem. Well, you don't need to write down the problem, but I do want you to write down the math to the problem. All right, so it takes Miss Mary 6 minutes, that's 0.1 hours, to drive 2 miles to the Caribou Coffee, and then an additional 25 minutes, or 0.4 hours, to travel to the remaining 16 miles to school. All right, so calculate her average speed in miles per hour. What is her average speed in miles per hour? So yes, I do want you to write down, you don't need to write down the problem, but write down this math. All right, so there's our problem. Let's calculate our average speed. How do we do this, right? So average speed is total distance divided by total time, right? So again, this formula I want you to write down. Yes, we have distance equals, or we have speed equals distance over time, but now since we're talking about an average, we want to make sure we put in the total distance and the total time. So these qualifiers, these adjectives matter. All right, so our total distance is 2 miles, right? Because we have that from the problem, 2 miles to the Caribou Coffee, and another 16 miles to school. All right, so that's our total distance. We need to divide that by our total time. Our total time is 0.1 hours and 0.4 hours. So a half an hour. Right? So how do we show our work? This is the part that I want you to write down. This is the part that I want you to write down. This is how to show work. Right? So formula is speed equals distance. Right? Formula equals speed equals distance over time. This T should be underneath here. See if I can get that fixed. It's not going to happen. Sorry about that. So this T should be closer to the D. So speed equals distance divided by time. Speed is distance divided by time. All right, so what's our speed? Our speed is 18 miles, and our distance is 5 hours. Now that's the total, right? That's the total, because we already figured out here that it's 1 hour plus 4 hours. So this would be like step 2 of your work. Then here's our final answer. 36 miles per hour. This is step 3 of your work, because we take 18 divided by 0.5. Right? So initially she drives kind of slow, and then she drives faster, but we're calculating the average. Pause from time to time when you need to. All right, so Does this mean she drives at the same speed all the time? Well, of course not. She speeds up and she slows down. She speeds up and she slows down. All right, so another sample problem to consider. Mr. Graves is driving to St. Paul for a concert. If he averages 55 miles per hour and the total distance is 70 miles per hour, how long of a trip will it be? All right, so now we have our speed. We have our average speed, right? And we have our distance. Right? Now we need to figure out the actual time. So again, all right, I'm going to pause this for just a second because this is bugging me. All right, students, sorry about that. Let's pick up where we left off. I was just bugging me that the formulas weren't turning out right. So, as we were saying, I wanted the S directly underneath the D. Our formula for time now is distance over speed. Right, we don't know the time. We know the distance and we know the speed. All right, so now this can be tricky. Right? This is where our dimensional analysis practice comes in. Right, so 70 miles is our distance, and our speed is 55 miles per hour. Now remember, so this is a whole number being divided by a fraction. And if you recall, from math, from algebra, if you're dividing a whole number by a fraction, you multiply the whole number by the inverse of the fraction. Right? So you multiply the whole number by the inverse of the fraction. And in that case, what ends up happening is the miles just cancel. So the miles just cancel, and we're left with 1.27 hours. Right? The miles cancel. 70 divided by 55 is 1.27 hours. Right? So that is our time. That's our total time that it took to travel. Right? So more on motion. All right. Difference between speed, constant speed, velocity. If an object always moves the same distance at the same amount of time, we say it is moving with constant speed. Right? Constant speed. But many objects, we know this, cars, airplanes, bicycles, longboards, right? The speed changes, and we have an average speed. Things slow down, sometimes things speed up, sometimes things are constantly slowing down and speeding up. So now we talk about the average speed to describe motion. We're using the average speed to describe motion. When the speed of an object is constantly changing, or even infrequently changing, the instantaneous speed is the speed of an object at a particular moment in time. So generically, we talk about speed at 55 miles an hour, or 60. You're driving at 60 miles an hour, you're driving at 70 miles an hour. If you look down at your speedometer when you're driving, whatever your speedometer tells you at that moment, that is your instantaneous speed. Sometimes you're driving 60 miles an hour, sometimes you're driving 70. Let's say it takes you an hour to go 65 miles an hour. Your average speed is 65 miles, but your instantaneous speed was whatever your speed was at any particular moment during that trip. Again, you may have to pause to go back and get this all written down, and that's fine. Oftentimes in physical science, knowing the speed of an object isn't enough. Right? Speed is just distance over time. But we have this additional concept called velocity. All right, so to know where an moving object is after a certain length of time, we require to know its speed and its direction. So I'm driving north at 55 miles an hour, or I'm biking southwest at 13 miles an hour. Right? We call this speed and direction velocity. So speed and direction is known as velocity. All right, so again, you don't have to write this down. You don't have to write this down, but just get your head around the concept. All right, so an airplane is flying from Minneapolis to Fargo, right? And it flies in a northwest direction, right? So Fargo is northwest of Minneapolis. The plane's traveling at 125 miles an hour, excuse me, but it's heading into a headwind of 25 miles an hour. So what is the velocity? What is the velocity? So there's our direction, there's our speed, so there's our velocity, but we have to compensate for this wind that is blowing into it, right? When velocities are different directions, you subtract, right? So take a second and draw this out. Take a second and draw that out. You don't have to draw a perfect little airplane, right? You can even just write the word airplane and put it in a box. Doesn't matter to me. But I do want you to write down Minneapolis, draw the little arrow, write down Fargo, label the arrow as 125 miles per hour, label this as the wind at 25 miles an hour, and then put that in there. When velocities are in different directions, you have to subtract. So what's the velocity of this airplane? Well, it's exactly what you think. It's 125 minus 25 miles per hour. So again, if you need to pause here, do for a second, but write down this simple graphic. And there's our answer. 125 miles per hour minus 25 miles per hour equals 100 miles per hour in a northwest direction. Again, technically speaking, this is just a speed, a distance over time. If we want to make it a velocity, we have to add that we're flying in a northwest direction. Okay, well, let's change it around. After discharging the passengers, the airplane leaves for Minneapolis again. This time, the wind speed is the same and the direction hasn't changed. Now, what's our velocity? Right? Now, what's our velocity? Oh, we're traveling at 125 miles per hour in a southeast direction. This time, we have a nice strong tailwind. When velocities are in the same direction, we add them. When velocities are in the same direction, we add them. So again, there's our distance plus the added wind. And because we're heading in a southwest direction, because we know or we're told we're heading in a southwest direction, it's considered a velocity. So again, write down this simple graphic. You don't need to write down this whole equation, but do write down this simple graphic. And write what's down in here, right? When velocities are in the same direction, we add them, and then put that down there. And again, we should probably add that we're traveling in a southeast direction. Almost done here. All right, so lastly, changes in velocity. This is the part that can be confusing to students. A change in speed or direction technically is a change in velocity. A change in speed or a direction, or both, of course. And where students get hung up on is they think a change in speed is definitely a change in velocity. Students forget that a change in direction is also a change in velocity, because remember, velocity includes speed and a direction. The rate of change is known as acceleration. Now again, here's where students can sometimes get hung up. In everyday conversation, we typically use acceleration as a term that applies to only speeding up. But in the strictest sense, acceleration also means slowing down. Because if you're slowing down, there's a change in your speed as you head in a particular direction. I know it's kind of goofy. All right, again, this relationship is this. Final velocity minus initial velocity divided by time. Yes, you should write all of this down. Again, if you need to pause it to get it all down, you certainly may do so. And just as a side note, you see indents here, indent a little bit. Or if it's labeled ABC, if I skip a line, skip a line. If I indent, indent. That keeps the information organized in your notes, and therefore keeps it organized in your brain. Okay, so a car can go from 20 miles to 100 kilometers per hour in 10 seconds, right? So again, we have really 2 units of time, right? We're driving 20 miles an hour at an instantaneous speed at some point. And over the course of 10 seconds, we've accelerated to 100 kilometers per hour. All right, so what is the acceleration? Let's calculate the acceleration. All right, so we have our final velocity, which is 100 kilometers per hour, minus our initial velocity, which is 20 kilometers per hour, divided by time. All right, so 100 kilometers per hour minus 20 kilometers per hour equals 80 kilometers per hour. Again, divided by 10 seconds. 80 divided by 10 is 8. And then with kilometers divided by hour divided by second. So it's 80 kilometers per hour, or 8 kilometers per hour per second. Now, that can be confusing to students. Just let me take a minute to explain what that means. Right? That means, so it's 8 kilometers per hour per second. Right? That means every second the car is going 8 kilometers per hour faster. So in the first second, it's going 8 kilometers per hour faster than it was the previous second. And the next second, it's going 8 kilometers per hour. All right, so again, let's think about our formula here. Second, at moment 0, we're going 20 miles an hour. 1 second later, we're going 28 miles per hour. 2 seconds later, we're going 36 miles per hour. 3 seconds later, we're going 44 miles per hour. So every second, we're going 8 kilometers per hour faster. Right, so that's our acceleration. And in this case, we're actually speeding up. Right? But remember, acceleration can also mean slowing down. I know we don't use the term acceleration on a daily basis to mean slowing down, but in the strictest sense, it does. So let's look at one of those problems. Quick question. Is the tip of the second hand on the clock accelerating? It's moving at a constant speed. But is it accelerating? The answer is yes, because it's a change in direction of motion. We don't have a change in speed, right? The second hand is very consistent on the speed, but it's a change in direction. If you're driving in a car and you've got it set on cruise control and you're going exactly 60 miles per hour, so your speed isn't changing. You're going 60 miles per hour. But let's say you're going around a corner or around a curve. Because you're going around a curve, you're always changing direction. That means that you are accelerating. Okay, so now let's take a look at what happens when we're slowing down. If an airplane has a landing velocity of 90 miles per hour, right? So now that's the speed, 90 miles per hour. The velocity is a direction. And it slows to a taxiing speed. So after it lands, it drives and pulls up to the airport, pulls up to the little hangars for people to get out. Right? We call that taxiing. Right? So it has a landing speed of 90 miles per hour, slows to a taxi speed of 15 miles per hour in 15 seconds. Right? Coming in at 90 miles per hour, lands, and then 15 seconds later, it's going 15 miles per hour. What is our change? What is our acceleration? Okay, so again, think of our formula. Right? Again, I want you to write this one down. Our final velocity minus our initial velocity divided by time. All right, so what's our final velocity? Our final velocity was 15 miles per hour. Our final velocity was 15 miles per hour in some direction. Our initial velocity was 90 miles per hour. That's what it was when we started to land, when we landed. Okay, so 15 minus 90 equals negative 75. And our total time was 15 seconds. Right, so we divide negative 75 by 15, and we come up with negative 5 miles per hour per second. Now again, we have 2 units of time there, hours and seconds. That can be confusing to students. What does that mean? Because it's negative, that just means that we're slowing down. Remember, technically our definition is any change in speed is acceleration. The negative means we're slowing down. So this means that every second we're going 5 miles per hour slower. Right? So at second 0, right when we land, we're going 90 miles per hour. 1 second later, we're going 85 miles per hour. Another second later, we're going 80 miles per hour. Another second later, we're going 75 miles per hour, and so on until we get to 15 miles per hour. Right? So we are slowing down every second. We're going 5 miles per hour slower. All right. That is it. Now let's put it into practice. As always, just a quick last note. Feel free to go back over these notes, watch the video again, and be sure to watch a supplemental video on the concept of motion and velocity.